Hello everyone, this is Ahmed from the University of Stuttgart, and now it is the time to check the three-dimensional visualization of lithium iron phosphate at different charge and discharge states. The aim is to study the microstructure distribution of all battery elements as a function of the electrochemical cycling. Lithium-ion batteries are considered the pioneering technology that has been successfully adopted for a wide range of applications, from portable electronics to the electrical vehicles. Furthermore, lithium-ion batteries market increases every year. Lithium iron phosphate LFP is a quite famous battery material that is characterized by its high specific capacity and long cycle stability. Using the ion beam sputtering, LFP layer is sputtered on silicon oxide substrate covered by platinum. The stack is then annealed in ultra vacuum at 500 Celsius. The crystalline structure is checked by the XRD. The electrochemical activity is checked by the cyclic voltammetry. In cyclic voltammetry, a potential window is swept with a constant scan rate, and the corresponding current is recorded. For example, here is a thin LFP film charged and discharged for 7,000 cycles, which is recorded. The capacity retention is found to be higher than 90% after than 7,000 cycles. The electrochemical performance proves that the LFP crystal is quite stable. After preparing the crystalline LFP, the LFP layer is charged and discharged. At the beginning, the film is initialized at a scan rate 1 mV per second. Then again it charged and discharged at a scan rate 0.33 mV per second for 20 cycles. The figure here shows the second cycle, the red curve, and the last cycle, the blue curve. At a specific voltage, the process is stopped. In this example, we stopped at 3.48 volt. The terminated voltage values depend on which phase I need to study. For example, at 2.8 volt is the fully lithiated LFP. At 4 volt is the fully delithiated phase FP. In between is the two phases LFP and FP. Then we apply a constant voltage, here in this example 3.48 volt. We apply it for 5 hours. The aim of this technique called chronoamperometry is to equilibrate the lithium ions through the whole layer. Using the left-out lamella method, the charged and discharged LFP tip was prepared. Here is a comparison between the crystalline LFP and its lithiation states at 70%. The two mass spectra are qualitatively similar. The measured concentrations are in good agreement with the nominal values. Lithium shows a new wavy profile, which hasn't been seen before in both amorphous and crystalline phases. This wavy profile may indicate some lithium heterogeneity. Here are the three-dimensional reconstruction for all elements, and only lithium component. Here only 1 nanometer slice is shown. The aim is to locate possible heterogeneity inside the LFP tip. Isocomposition surface plus the two-dimension maps of only lithium element display some concentrated lithium regions. To get further microscopic details, two-dimension density maps plus the isodensity surface confirm the heterogeneity. The aim is to study the LFP at different lithiation and delithiation states. Lithiation and delithiation mean discharge and discharge of LFP. The cyclic voltammetry curve shows here the terminated voltages. We have different films with different charge and discharge states. To calculate the lithiation states, cyclic voltammetry curve is converted to the time scale. Lithiation state can be identified as the ratio between the areas of the last half cycle and 1 half cycle before. A charged and discharged LFP at different lithiation states were measured by atom probe tomography. Lithium in all states except the 100% shows the wavy profile, which indicate the heterogeneities. Lithium amount as compared to the expected contents are shown. Lithiation of the fully dilithiated phase ends by filling up all available sites, which is reflected by getting the completed lithium amount. By contrast, dilithiation of the fully lithiated phase records a higher amount than what was expected. This lithium excess in the fully dilithiated phase may be described by inactive LFP region inside the grains. Existing of such high amount of lithium at the fully dilithiated phase proves that the LFP lithium iron phosphate isn't entirely transformed to the FP iron phosphate during the dilithiation. This is compatible with the radial model. The concept of the radial model is that either the fully lithiated phase or the fully dilithiated phase is initially formed from the surface, while the phase boundary moves to the core. When the LFP is being dilithiated, a lithium deficient shell wraps around the lithium rich core, resulting in shrinking of the core and expanding the shell. Moreover, dead LFP cores at the end stage is proposed. When the limited mobility of the lithium ions through the interface can't sustain the current density, the electrochemical reaction stops without fully consuming the LFP. Here are the LFP density and lithium density of the fully dilithiated phase in this study. The highlighted regions represent the dead LFP phase inside the FP phase. In order to check the homogeneity and possible phase separation, a frequency distribution analysis was applied. A region of interest from the reconstructed volume is partitioned into small voxels. The size of the voxel may be defined either by constant volume, in which the number of atoms per voxel is varied, or voxels with a constant number of atoms, whereas its sizes are varied. Chi-square measures the departure of the observed frequency distribution from the binomial distribution. To normalize chi-square on the sample size, the percent coefficient was introduced. In this study, a rectangular pattern and a rectangular with dimensions 20, 20, 60 nanometer cubic was used to calculate the frequency distribution. Here are the frequency distribution for lithium element at different lithiation states. Events were divided into bins of 150 atoms per voxel. The composition was calculated for each bin and plotted in a histogram form. Percent coefficient values range from 0 to 1. 0 indicates a uniform distribution of lithium element, and 1 indicates a statistically relevant segregation. The percent coefficient value increases as the lithiation states increase, then decrease again at the 100% of lithiation state. The same trend is shown for the broadening of the observed frequency distribution, which indicates segregation. The percent coefficient evolution versus the lithium composition and the lithiation state are summarized here. The green line represents the expectation. As the lithiation state increases, lithium composition and its segregation increase. A low percent coefficient value is observed for the fully dilithiated phase. This indicates a homogeneous lithium distribution, as expected from the phase transformation curve. With further increase of the lithiation state, the percent coefficient value increases as a result of existing the two phases. At the highest lithiation state, a homogeneous distribution is expected. The percent coefficient value here decreased, but still doesn't show the homogeneous distribution. The percent coefficient value confirms the existing of another phase. This can be clarified from the electrochemistry curve. This point, the 100%, means the crystalline LFP before charging and discharging. The cyclic voltammetric curve shows a tiny peak at 2 volt that represents an extra phase. That's why the percent coefficient value showed a higher percent coefficient value than what was expected. The percent coefficient evolution versus the composition of iron, phosphorus, and oxygen and lithium states for all of them are summarized. Opposite to the lithium element, percent coefficient for iron, phosphorus, and oxygen show almost no change. Thereby, iron, phosphorus, and oxygen tend to be unaffected during the delithiation or lithiation process. Iron, phosphorus, and oxygen prove suitable linkages between them, which draw the great crystal stability of LFP. Conclusion: the capabilities of atom probe tomography in studying lithium iron phosphate at different discharge and charge states were checked. Inactive lithium iron phosphate regions in the fully delithiated phase iron phosphate were experimentally highlighted. The results provide a guidance to statistically understand the local microstructure evolution in battery materials. On the other hand, atom probe tomography showed some difficulties to study the interface between the two phases. Thank you for your attention. I hope I have added something new for you. Bye.